All right, seems to be working. Okay, here we go. We're going to start off 2.8 by talking about this definition of this phrase called similar figures. Similar figures. Anybody have any thoughts about what similar figures might be? If you had to take a guess. Will, what do you think, buddy?
Big, like, shapes that are the same size, but they're like equivalent to each other.
Okay, you're on the right track. They're kind of equivalent to each other. Is everything similar to everything else? Like, am I similar to you?
Yes, you're both humans.
Oh, you're both humans. All right, okay, fair enough. So yeah, so we have to be very distinct as to what we're talking about, right? Is a bicycle similar to? Where'd it go? Where'd it go? It just like totally disappeared. There it is. That's the word. Okay, is a bicycle similar to a car?
Yes, they're both transportation.
So you would say yes, right? Because they're transportation. So some would say yes, some would say no. Well, one takes gasoline, one doesn't, right? So I mean, it depends on one has a steering wheel, one has two wheels, one has four wheels. Depends on one has a motorcycle. Okay. So we have to be very, very careful as to what we talk about by similar figures. Okay. So for us in mathematics, okay, if something is similar, then the definition that we're going to use is going to be this one. I hope this works. It's going to be it's going to have the same shape, okay, but not the same size. Not the same size, okay? And the first thing that I thought of are two figures that were similar is the iPhone 6 and the iPhone 6 Plus. Right? They are the same shape. They are different sizes. Those are similar figures. I think everyone in the room can understand that if you've seen pictures of them, right? I saw in a magazine where one was right next to each other and they're advertising as actual sizes, you know? And there it is, right? That's exactly what I mean by similar figures. They're the same exact shape. They are just different sizes, okay? So I try maybe thinking of like a penny and a quarter. Right? They're both circles, they're different sizes. Okay, so they're similar figures. So they're going to have the same shape, not necessarily the same size. Okay, so why do we care about this? Okay, we care about this because we can use proportions. We can use proportions to find missing side lengths in similar figures. Okay, so is it good that we know about proportions? Yes, because we just learned about proportions in lesson 2.7. We learned about proportions. It was just two ratios that equal to each other, and we solved it using cross product, and we proved it. So we know about proportions now, so we're building and building and building, okay? So let me talk to you about this shape, this word right here, similar figure. Okay, so ladies and gentlemen, take a look. I have two triangles on the screen for you. I have a smaller triangle, which, you know what, we can be cool. We can color this in yellow, okay? So I have this yellow triangle over here, and then I have this other triangle, which we'll color in green over here. And I got a lot to take up over here, so it looks like green. All right, so I have the yellow and I have the green, okay? I'm claiming to you that these two figures are similar figures. So what's the definition again that we're going to use? Let's go back to box number 1. It is what? Same shape, not the same size. So would you agree that these are the same shape because they're both triangles, but they're not the same size, right? Everybody cool with that part so far? Okay, so let's go back to 100%. Okay, so what can we now say about these? Okay, well, if they are similar figures, we can make this statement right here, okay? So I'm going to make triangle ABC, that's the yellow triangle, triangle ABC, okay, is similar to, okay, similar to is a squiggly line, it's like a sideways backwards S, okay, is similar to triangle DEF, okay, so this symbol right here, that is the symbol for similar. Have you guys ever seen that symbol before? Yeah, so okay, you saw me right. Yeah, approximately is the two equal sign. So this is approximately, right? That's that one. And that's for like, you know, the square root of 2 is approximately 1.41. This is similar. This means like with figures, okay? All right, so if I'm claiming that these two are similar figures, then we get something for that information. We get to pull some information out of it. And here's what we are allowed to say, okay? We can say this. We can say that their side lengths 8/12. So check it out. I said that this side length to that side length, okay? See that I've created a ratio between their corresponding side lengths. How come I didn't say like 8/15? How come I didn't say that one?
Because they're not the corresponding.
That's not corresponding. It's not in the same spot, right? Not in the same spot. So I do 8/12. I'll pick a different color for you guys, make this really obvious, okay? 12/18, right? Has to be equal to 12/18. Ooh, what's the last one I'm going to claim here? In purple. What's the last one I'm going to claim, everybody? 10/15. Has to be equal to 10/15. So what are we creating here? If we have similar figures, then their side lengths are in proportion. I'll say that again. If I have similar figures, their side lengths are in proportion, okay? So right now, how much is 8 divided by 12 on the calculator? What would that be? What's 8 divided by 12 on a calculator? Who's got it? Bust it out for me real quick. 8 divided by 12 on the calculator. 0.6666, repeating, right? Okay, good. What's 12 divided by 18 on the calculator? 12 divided by 18. What? Okay, what's 10 divided by 15 on the calculator? 0.6. Okay, so check it out. Similar figures give us side lengths that are in proportion. And look, we just proved it to each other right now, okay? So similar figures give us side lengths that are in proportion. Okay, so check this out. Here's the situation for this example about solving proportions using similar figures. We have the sun shining in the sky. We have a building with an awning and a little table outside. And then we have, me hanging out. So as we know, the sun shines down and it creates a shadow on the ground for both figures, right? Like my shadow there, it's in gray. It creates a shadow for both figures, okay? If I can measure, I'll move this up a little bit. If I measure the length of the shadow, I get a length of 15 feet, okay? If I compare the length of the shadow to the building to the length of the shadow of the person, I get a length of 3 feet, okay? That's my shadow there. Now, I know how tall I am, or this person is for this example, and this person is 5 feet tall. I'm actually taller than 5 feet for the record, but this person is 5 feet tall. And I am interested in the height, which I'll call h, of the building. So I am taking advantage of similar figures, okay? And I am claiming that we are the same shape but not the same size. The shape that I'm claiming is that we are just vertical. That's all I'm saying, right? We're vertical, right, for this part. So the question is, what kind of proportion can I set up? Okay, I need to set up a proportion. So I need to compare what to what versus what to what. What would be a good idea to compare? Anybody got any ideas here? Yeah, Daniel, what do you think, buddy?
The building to the shadow of the building equals the person's height.
So the height of the building, which I'm calling h, to the shadow of the building, right? Which we'll just go, shadow of the building, has to equal the height of the person to the shadow of the person. Shadow of the person. Does that make sense? So he's comparing the height of the building to the shadow of the building, to the height of the person to the shadow of the person. I think that's absolutely perfect. So what do we know here? I don't want blue, I just use blue. Let's use orange. Okay, the height of the building, that's the thing that I'm looking for. The shadow of the building is how much?
15.
It's 15 what? 15 monkeys? Oh, it's 15 feet. Okay, good. And then I want the height of the person. How much is the height of the person? That is 5 feet. And I'm comparing that to the shadow of the person, which is 3 feet. Okay, so before we even solve this using cross products, does the answer have to be more or less than 15? And how do you know? Has to be more. How do I know that it has to be more? There's something about this proportion that tells me it has to be more. What is it going to be? Yes, Alice.
The shadow of the person. Wait, just kidding. Never mind.
You are I think you're on the right track. Will, what do you think, buddy?
The height of the person has
right? They have to be in the same ratio, right? They have to be in the same ratio. So since 5 is bigger than 3, and 5 is the length of the person, then the height of the building has to be bigger than the shadow. So I know it has to be more than 15. So if I get an answer and the answer is 2, I did some algebra wrong, right? So it's okay to think ahead and plan ahead, right? All right, great. Now that we know the answer should be more than 15, what can we do?
Well, if you don't actually want to do the multiplication, okay, so it's 25 if you do, but if you don't actually want to do it, you can just multiply the 5 by 5. Because 15, 3 times 5 is 15.
Absolutely. We have many options that we can do. I'm going to go ahead and use the cross product because that's the part that we're trying to work on. But you are absolutely right. There are more than one ways that we can do this. So I'm going to use cross product, and I get this. I get 3h is worth 5 15s is 75, right? I think so. 75. And I'm going to then divide by 3. So I'm going to get the height of the building is 25 feet. And that's more than 15. And that's what we came up with. So we are claiming that these two similar figures are in ratio. We're claiming that 25 over 15 is the same ratio as 5 to 3, and it is.